Okay.
Did you say that this photocopy was
Whoops.
by
I don't know why that
time?
didn't. What's that?
By how much time?
Okay. Well, yeah. I mean, where speed is distance divided by time, but the distance is actually measured by the time because you know the RPM of the machine. So RPMs is the revolutions per minute, right? So if you have so many RPMs, if you know the circumference of the piece, there's actually two different routes we can go with this. One is on a lathe turning. Then you're looking at the circumference of the material. Or you can look at a mill. And on the mill, it's the circumference of the tool. So we're going to let n equal the number of RPM. The number of RPM times the circumference of the tool or the material is equal to the speed per minute. Why do I say speed and not just distance? Well, because RPM is per minute. That's how far it goes in a minute. I should put speed, I'll put distance per minute. And since it's per minute, that makes it a speed. So let's say that we have, let's look at a lathe. We are turning a 2-inch piece of material. And we're moving at 300 RPM. What is its speed here, the surface of that material? Well, the circumference is how much? Well, the diameter, remember, circumference of a circle, the diameter is 2 inches. So the circumference is not 4. Radius doubled would be diameter, but we have the full diameter. Pi times diameter. So pi times 2. Problem is, 2 is measured in what units? Inches. Surface cutting speed is measured in feet per second. So divide that by 12. Then multiply by our RPM, right? To get a speed. So for this one, pi times 2 times 300 RPMs, divided by 12 to make it into feet, is what? 157 feet per minute. Is that what you come up with? So the formula, surface cutting speed, is pi times the diameter times the number of RPM divided by 12. Now, many of you may have seen an approximate formula, diameter times RPM over 4, or sometimes over 3.8 something. Does that sound familiar? Have you guys used that approximation at all? 3.82, yep. The 3.82 is just 12 divided by pi. That's all that is. This is often used in industry just because it's quick to calculate. And when you divide by 4 instead of 3.82, you're going to underestimate the speed, so you won't do any damage, at least at that speed. And you can always just slightly ease it up to, if it's not cutting well. The only time cutting too slow usually is a problem is you're dealing with soft metals like aluminum. Then cutting too slow can be an issue. So in your notes, find the surface cutting speed, 400 RPMs on a 1 1/4 inch piece. So we'll set this up. Our surface cutting speed will be pi times 1 1/4 times 400 divided by 12. 131, very good. When we're dealing with RPM, by the way, round to the nearest whole RPM. If we're dealing with size, we would round to the nearest thousandth of an inch, unless told to go to a 10,000th. That's not RPM, that's feet per minute, right? I don't know why I labeled that RPM. Apparently, that's where we're going next, is going to find the RPM. Usually, you don't just set an RPM and calculate a surface cutting speed. Usually, you're told, hey, I'm going to look up for this material. For this material, the recommended surface cutting speed is 180 feet per minute. And I'm going to turn a piece of material that has a diameter 3/4 of an inch. You want to find the RPM, find N. Well, this is where our algebra skills come in handy. C equals pi dn over 12. To solve for n, I would multiply by 12, right? And then do what? Divide by pi d, right? Does that make sense? So what I've done is rearrange this formula. 12c over pi times d equals n. Now again, you guys might have seen 3.82 times your cutting speed divided by your diameter. If you guys want to use that formula, it's the same thing. So for this piece, 180 is our cutting speed. So 12 times 180 over pi, 3.14, times our 3/4 inch diameter is going to give us our RPM. Now here's where you got to be careful punching this in the calculator. You got to do one of two things. Either when I hit divide here, I've got to put in parentheses, 3.14 times 0.75, and then close my parentheses. Or you've got to just divide by each of them. Because they're both on the bottom of the fraction, you're dividing by each of them. It's simpler for me to put them in parentheses like this so that it looks better. It looks the way it does in the problem. If you don't put parentheses around them, it's going to really screw you up. So I get 917 RPM. Now that seems like high RPM, but 3/4 of an inch is a relatively small diameter. So you've got a material with a recommended surface cutting speed of 120 feet per minute. You are going to cut through it with a 1/2 inch mill. In your notes, find the RPM you'd set your mill at. So what'd you come up with? So N equals 12 times 120, right? Divided by 3.14 times 0.5. So 12 times 120 divided by, make sure I put in my parentheses, 3.14 times 0.5. 917, yeah. What, do you think that was funny? I changed the 180 to 120 and the 3/4 to 0.5, which cancels each other out. So what if we have a machine running at 300 RPM, turning material with a diameter of 62 millimeters. Find your surface cutting speed in meters per minute. The only thing that's changed here is the units. My cutting speed is still going to be my distance, which is going to be pi times my diameter times my RPM. But now instead of converting inches into feet, I have to convert millimeters into meters. How many millimeters are in a meter? 1,000. So this will be pi times 62 times 300 divided by 1,000. So 3.14 times 62 times 300 divided by 1,000. 58.4, what you getting? It is actually kind of easier. Yeah, you can just move the decimal point, but so divided by 1,000. Yeah. So let's say you're running at 150 RPM with a 34 millimeter mill. Find your surface cutting speed. So let's take a peek. Pi times 34 times 150. 1,000. So 3.14 times 34 times 150 divided by 1,000. 16 meters per minute. That's a little slow. That's roughly 50 feet per minute. That's running a little slow. But you noticed I made the RPMs lower and the tool smaller, the diameter smaller. Well, once again, we want to rearrange this so that we can find RPM for N. And again, the only difference is 1,000 instead of 12. So instead of multiplying by 12, I'm multiplying by 1,000. And still dividing by pi times diameter to get my recommended RPM. So let's say that we have a material that recommends a surface cutting speed of 60 meters per minute, and we're running it with a mill that has a 45 millimeter diameter. To find the RPM, it's 1,000 times 60 over 3.14 times 45. Now you notice that time I forgot to put in my parentheses before the 3.14, so instead of multiplying by 45, I had to divide by 45 again. Because they're both on the bottom of the fraction. It works out the same. 424.6, so 425 RPM is what I'd run that at. Is that what you guys come up with? Let's have you guys try one. We're going to mill, or we're going to turn a piece of 38 millimeter stock with a recommended surface cutting speed of 55 meters per minute. In your notes, find your recommended RPM. So 1,000 times what? 55 over 3.14 times 38. Again, note that I had to put parentheses around that so I could get it on there. 461. Okay, well, the next step in all this is figuring out how long it'll take. Now, let's say that we're cutting into a piece of material here with a mill. Okay. One thing with a mill, it depends on the number of teeth you have on the mill. Now, we're not going to account for the number of teeth on the mill, because a lot of times you get a surface, a feed rate of like 0.0015 inches per cutting surface, or edge, is what it's often called. Per tooth, yeah. If you have a mill that has 2 cutting surfaces or 2 teeth on it, then you get double that per revolution. You had 3 cutting teeth, you triple that per revolution. What we're going to do is we're just going to do it this way. The feed rate is just given in inches per revolution. So we're going to assume that the number of teeth on our tool has already been taken into account there. You know, so this would have been, if this were your feed rate per edge or per tooth, that would be a 2-tooth mill. That's already been accounted for. So what this means is the distance traveled is equal to a rate times time. Well, the rate is what we're looking at right now. This is not a rate. I mean, it is a rate, but it's not a speed. The speed here, or the rate that we are looking for, is the speed this tool is going to advance across the material. And that speed is the inches per revolution, which we call the feed rate, or F, times the number of RPM. If this tool here is 200 RPM and has a feed rate of 0.03 of an inch per revolution, then it is going to advance 200 revolutions. RPM, remember, means revolutions per 1 minute, times 0.003 inches per single revolution. Now notice I'm writing it out the long way just to show you revolutions cancel out here. 200 times 0.03 is 0.6 inches over 1 minute. That's 0.6 inches per minute. So that is giving us a speed. So then the distance it can travel would be that speed times the time. Well, we don't necessarily want to know the distance traveled. We know the distance we need to travel. We want to find the time. So we're going to divide by the rate. The time is equal to the distance divided by that rate. So our time required is going to be the length of the cut, which is our distance, times our feed rate, or over our feed rate times our RPM, which is our speed that we're going, the rate of motion. Does that look familiar? So let's say that we have a material that allows us to have a feed rate of 0.04 per revolution. We are turning at 150 RPM. And we need to make a 6-inch cut. How long will this take? Well, time equals length over F times N. Our length is what? 6 inches. F is 4/1000th of an inch per revolution, and N is 150. Do all our units match up? In other words, do all our lengths match up? 6 is measured in inches. F is also measured in inches per revolution. So our units do match up. So we're good. So on this one, when I type it in the calculator, I have to do 6 divided by, then in parentheses, 0.004 times 150. Close my parentheses. And we get 10. What's that 10 in? Minutes. The only time we have in this problem is the minutes from the RPM, revolutions per minute. So it would take 10 minutes to advance across that 6-inch piece. 150 RPM is a pretty slow turn, well, depending on the tool. That's assuming that's probably a pretty hard material we're dealing with there. What's that? Sure. So if I give you a feed rate, 6/1000th of an inch per revolution, RPMs of 250 RPM, and we have to make a cut that is 4 inches. In your notes, tell me how long that's going to take. So what goes on top of our fraction here? 4 inches. On bottom, our feed rate is 0.006 and our RPM is 250. So 4 divided by parentheses, 0.006 times 250. 2.667 minutes. Or 2 minutes and 40 seconds if you wanted to convert it. So let's say we have a material that is rated for a surface cutting speed of 180 feet per minute. We have, or we are using 7/8 inch mill, and we need to make a cut that is 8 inches long. How long is it going to take to make that cut? I want to give you guys a minute in your notes. See if you can figure that one out. Where do we start here? Finding the RPM. Very good. So what do we do? $12 times 180 feet per second, 12 times our cutting speed over pi times our diameter, 3.14 times 7/8. So 12 times 180 divided by parentheses pi, or 3.14, times 7/8, close my parentheses. We get 786 RPM. Now what? Our time is going to be our length of cut. I didn't give you a feed rate, did I? No. It would make more sense if I gave you a feed rate of 0.005 of an inch per rev. So now that just means over here it's going to be 0.005 times 786. So 8 divided by 0.005 times previous answer. 2 minutes, 2.035 minutes. So about 2 minutes and 2 seconds. Sorry about that. Didn't realize I didn't give you the feed rate there. So let's look at this. Let's say you need to run 300 parts. Assume 0.3 minute setup per part. To load and unload the machine takes about 18 seconds. Okay? Surface cutting speed for this material, 120 RPM. We're going to have a diameter. One and a quarter inches. Each part has a 3-inch cut. And a 0.004 of an inch per revolution cutting speed. How long is it going to take to run this set of parts? Now I'm going to go through it slowly so you guys can try to stay a step ahead of me here. We're running out of time, otherwise I'd give you a minute or two to run it on your own. But the first thing we're going to find is our time per part. So the cut time per part. And to do that, we first need to know the RPM. So RPM is going to equal 12 times our surface cutting speed of 120 RPM divided by 3.14 times our diameter of 1 1/4. So 12 times 120 divided by 3.14 times 1.25. 367 you coming up with for your RPM? Yes, no? No?
No, I got like 5,000.
So 12 times 120 divided by, make sure you put the 3.14 times.
I multiplied it, sorry.
Okay,
I changed one number and I took my points to the...
gotcha. So we're at 367 RPM. So that means our cut time per part is going to be our 3-inch cut divided by a 0.004 of an inch per revolution times 367 RPM. So 3 divided by 0.004 times 367. 2.044 minutes per part. Now from here we're going to add the setup. We have 0.3 minutes for setup, so now it's 2.344 minutes per part times 300 parts. So it's going to take 703 minutes, 703.2 minutes. Divided by 60 will make it hours. 11.72 hours.
And
So basically, you're looking at 11 3/4 hours. I'd probably schedule it as a 12-hour job. Just have some machine set up.
I have 20 cycle time.
Okay.
I have 300 parts. And about 6 bonds of the 4 hours. Or 20 cycle time, 10 parts, and 5 parts per 20-minute cycle time.
So there's 5 parts in that. So that means you need 60 cycles, right?
Yeah.
So take 20 hours.
Yeah.
Fun. In your packet that I just passed out earlier today, on page 242, 1 through 57, the odds are looking at surface cutting speeds and cut times and feed rates and all sorts of good things. Today is the 8th, yes. One through 57,